Okay, we've talked about Newton's laws and how to analyze the forces and calculate a few of them. We'll go over plenty more. We have spring forces to go over, frictional forces and such. For this first test, we'll keep it with some basic forces though, but we do need to know how to represent them properly. So let's figure that out. We can draw forces directly onto a diagram like this and say we have some mass times gravity pointed down, some normal force pointed up, but that's not a free body diagram. A free body diagram, we need to represent this mass as a point. And then we would say, okay, we have a normal force pointed up due to the table supporting it, and some mass times gravity pointed down. These would be equal length if it is not accelerating and it is sitting at rest, right? Another example, I'm going to do this inclined plane again because it's pretty oftenly missed, or it just doesn't click right away for a lot of people. I know it didn't for me when I was younger. If we had some mass, and this will only be adding to this problem, and I mentioned that before, we can add a set of pulleys and attach it to a mass hanging over here. Well, for now, let's just figure out how to draw a free body diagram on an inclined plane, and that's what this is. So a free body diagram for inclined plane. Free body diagrams are where we get Newton's second law equations from. We get our equations of motion from the diagrams. We must be good at these. We can draw on the picture, but you need to represent all the forces going through one point. And there's a reason for that, and I'll talk about it briefly because we'll talk about it in depth later. A force through a point will cause, if this is a force, it's going to cause a mass times its acceleration in that same direction. However, if I put a force through some other point, some distance d away from the mass center, it's going to cause this thing to rotate. It's going to give it what's called a moment or a torque. Right now we're not dealing with that. We have Newton's second law for moments, but we are not there yet. So let's just deal with all of our forces being what's called concurrent through the mass center. So on an inclined plane, I tend to like to draw the forces directly on the diagram just because it's easier to make the perpendicular, to make the parallel line and such. But the first thing I always do on my inclined plane is draw mg pointed straight down. It isn't a gravitational field, therefore it has some mass times the acceleration due to gravity pointed down. Now what I need to do is make a parallel to this and a perpendicular through the mass center that makes a right triangle. This angle theta becomes this angle theta up here, and if you do some SOHCAHTOA, we find out that this is mg sine, or mg cosine theta, and this component right here, so let's put the components on there, is mg sine theta. So this is the component of the weight that's going down the plane. The mg cosine theta is the component of the weight perpendicular to the plane, and that's the one that corresponds to our normal force. So that's our Newton's third law right there. We might get to the point where we have friction. If we did, we would say it opposes motion always. We're not at that point, but let's say the block was moving up and to the right. Friction would then be drawn in the backwards direction. You can label it the force of friction. If this was moving up and to the right, like the brown arrow shows right here, maybe that's due to some pulley and some force right here pulling down on it. Well, that's equal to a tension, and that's also going through the mass center. So we are going to deal with tensions now. We do need to know how to deal with it. And that brings me to my point on pulleys. We need to know how pulleys work. All pulleys do is change the direction of force. It is a simple machine, and of all the simple machines, that's all they do. For instance, a screw, right? If I had a screw, screws require a twisting force, but we end up getting a downward or upward motion. A wedge, I can give a wedge like an axe, for instance, a force in this direction, and it causes the wood to split in this direction, right? What else? There's plenty of others, like the wheel. The wheel turns a rotational motion into a horizontal motion. But all a pulley does is change the direction of force. So let's say I have a ceiling, and from that ceiling, let's draw a vertical line. From that ceiling, I have a pulley holding a mass. And I'm applying a force right here to hold that mass up. We'll learn how to calculate that. One, we can apply a free body diagram to it and then solve Newton's second laws. But what we need to know is that and I mentioned this once already, in a rope or something that supports a tension, the tension is the same in the rope everywhere. If we have one rope, the tension is the same everywhere. So here's another example. What if I had a table, we have a pulley, and maybe we have some mass attached to the pulley, and I'm pulling down with some force. What we need to know is that this force is, the pulley is just changing the direction of the force. The force was originally in this direction, but we're going to be able to apply that same exact magnitude of force now in what's called the x direction. It just changed the direction for us. And for all of our problems, our pulleys will be weightless, so they don't have a moment of inertia, which we'll learn about. Which, right, it takes some oomph to spin something. It doesn't spin freely. Well, these are going to spin freely. They're going to be weightless and frictionless. It makes problems easier, so we can learn the fundamentals, and then you'll get to the harder stuff in your future. Something that's commonly misconcepted. What does the free body diagram of an object in free fall look like? Think about it for a second. So if we have some baseball, or it could be a satellite going around Earth, which is actually in free fall, it has only the force of gravity acting on it, then we have only one force, the force due to gravity. And if it's close to the surface of Earth, we'll call that mass times gravity. In this case, if we wanted to put this into vector form, the force due to gravity is equal to mass times gravity. Those are both scalar quantities, and we'd have to give it a direction. I would say the minus j direction. So all of these can be turned into vectors just by giving it the proper direction. And trying to think of any other scenarios. We're going to be dealing with springs and friction, but not till next test, so I don't want to overwhelm you. I'll do another pulley problem, because pulley problems tend to confuse many. I teach dynamics. We do a lot of pulley problems in there, and that's not something that comes easy to most. What if we had a pulley that was mounted on the ceiling, And let's say there's one string, and on this we have a mass. With our hand or something, we apply a downward force on this side. Well, all the pulley does is apply the same magnitude of force. Let's call that F1. Well, it applies F1, but in the opposite direction of the original F1. Free body diagram for this scenario, I would represent the mass with a point, and I would say that we have a tension pointed up, which was equal to our force 1, or opposite, right? It's not opposite actually. Just get the direction from the diagram. In this case, relative to our mass, it's pointed up. Up we're going to call positive, so let's call it a positive tension. And that's equal to the positive F1. And then we have the mass times gravity of the object hanging down. So the force due to gravity would be mass times gravity. So two forces on this object. On an object in free fall, we would only have one, just the force of gravity. And if this force is being applied right here, we cannot simply say that it is in static equilibrium and that the tension is equal to, we cannot say that the tension is equal to mass times gravity. Don't get used to that. Sometimes it is. If this was hanging just from the wall and was in static equilibrium, then absolutely, this tension right here is going to be equal to the force of gravity, or mg. They're exactly the same magnitude, but opposite directions. If we have motion, though, if there's an acceleration, then that does not apply. We cannot say that the tension is equal to mg. We have to apply Newton's second law. We have one body on here. We could say the sum of the forces in the y direction on this body would equal some mass times acceleration. Assume it accelerates unless they tell you it's at rest, and then we put our forces in. We have a tension going up. We have mass times gravity going down, and that's going to be equal to some mass times acceleration. Now check it out. If we solve for the tension, it does not indeed equal mg. It equals the mass times the acceleration plus mg. Please don't forget this. That's a very important one. Okay, thinking of any other scenarios that we need to deal with at the moment. I've done the inclined plane a few times. Alright, start diving into the homework and see what you can do.